I would like to welcome Dr. Breda O'Dwyer, who is the head of SEED and senior lecturer in entrepreneurial learning and practice in Munster Technological University. They are a key partner here in the John McCarthy AI Summer School, and Breda will intro and facilitate the discussion with our next speaker today. Breda, over to you.
Hi, Raideen. Thank you very much, and good afternoon, everybody. It is indeed very, very enlightening so far, and I'm sure a lot more to come. So I'm delighted here to have the opportunity to introduce Dr. Morten Goodwin, who is a professor at the University of Agdar in Norway, and he's also the deputy director there for the Centre of AI, Artificial Intelligence Research. And I guess apart from lecturing undergrad, masters and PhDs, I think Morten also has a lot of publications to his name, and most recently the book that he wrote on AI for the Myth of Machines. And forgive me, Morten, I will not attempt to pronounce this with my fast Kerry speed accent in Norwegian. But very much welcome here today to the John McCarthy AI Summer School. And I guess we're all very much looking forward to the talk, which is fundamentally about the obvious secrets to making AI for wellness. May I remind those who are joining us in this session to please pop your questions into the Q&A function, and we'll return after the presentation with Morten and share those questions with him and learn even more. So for now, Morten, it's over to you, and welcome again.
Great, and thank you for introducing me, and thank you for inviting me, and thank you for finding a picture of me that I took first day of high school as representation there. So I'm going to talk about AI, of course, and I'm going to talk about some of my work and what is going on, how can we do that for wellness, what is the real secret to making AI and machine learning and deep learning really valuable for users, really valuable in healthcare, and really valuable for the community as a whole. And I'll share my screen. Hopefully you can very soon see the screen, and someone will shout out if not.
No, it's good. Yeah, we can see it. Thank you.
Great. And ultimately, of course, what I'm supposed to present is the secret to making AI for wellness. So my field of work is in machine learning specifically, and more specifically that of deep neural networks, that type of technique that mimics the human brain, and that has been had a lot of attention the last years. And as probably some of you know, the idea of a neural network is can be quite complex, and it has existed for a lot of years, but it is the recent advances that has really made a difference in the application area of neural networks, both in research and in what is done in real life. And one key aspect of what is really happening here is that for the first time in history, I would say, there's a very, very short distance between research and practical usage. So, for example, some years ago, there was this open Kaggle competition on trying to do automatic diagnosis from image recognition on the disease diabetic retinopathy. So that is a disease that affects a lot of people. It affects people with diabetes, and it is not that tricky to diagnose, but it tends to be diagnosed too late because people don't there's not enough capacity, etc., to make this really work in practice. So a couple of years ago, there was this competition, and it turned out, as many of these high-level presentations are, the AI was able to not only beat other types of algorithms, but also beat doctors, medical doctors. And then there's a lot of hype, of course, what really happens. Do we need medical doctors? All of those things. And we, of course, know that that's mostly just hype. These tools are exactly that. Those are tools, but those are tools that come from the research area and then very, very, very quickly goes into the practical use as well. So in this example, this was an open competition. People were supposed to submit their algorithms, and the deep neural network image classification methods won the competition by far. Many other competitions as well. This was one that has at least a lot of attention. What happened? Well, 2 or 3 years later, the same type of AI was put into practice among other places in rural India. So in India, there's sometimes lack of medical doctors. 70 million Indian people have diabetes. Often it is hard to get access to the patient record, and then this type of AI tool that turned out to, then some people claimed were just a way for researchers to play and have fun and make games, had a real impact for real life Indian people. And this is exactly what we see in a lot of AI research. We see research that kind of solves a relatively minor task, but then we see it very closely related to actual application areas in health, in game playing, in in agriculture, all over the place. It comes from the AI. So what used to take years before it went from academia into real use of users can now only take so few years or even months in some cases. And that is kind of what I see as the big strength of the AI research that is really happening. Most of the techniques, most of the methods have a long history. Of course, there's methodical changes that has happened in recent years as well, but it is much about getting access to bigger data sets. It's much about getting access to faster computers, and it's much about the awareness that AI can actually solve and help in real cases. And then that matters for many people, not only those that are interested in academic research. So we're a group that we've been doing AI research for 20 years or so, but in 2017, the AI hype was at its highest, and then we started this Center for Artificial Intelligence Research. This was the day we opened it. We were very happy because that's what you are when you open a new center. And 2 years later, 2019, we had grown to this size. And in 2021, we've of course grown much more, but then we don't meet physically, so we don't have a picture from that. And we run AI Research Center that does not only work on fundamental AI research, but we do a lot of collaboration with hospitals outside in Norway. We do a lot of research across universities in Norway and in Europe in general. And health is one of our ideas of working. In the Norwegian system, there's a lot of other universities working on the same type of technology, and the universities of Norway have had this idea that they should all join forces together and make a big center together, and that center is called NORA. So all Norwegian universities and all publicly funded research centers have joined this consortium, NORA, and so that we have the AI strengths together. So I see that as a kind of strength of the Norwegian AI research, meaning that we have we're all trying to push the same wagon in a way. We're all trying to make the same research there. Additionally, we have a building that is meant for measuring AI, measuring patients, measuring and surveillance of patients using AI. So meaning that it's very often hard to get access to hospital data for privacy reasons, for example. It's very hard to get access to hospital data from other universities because when you cross, the data crosses lines, it causes problems. GDPR is one reason for that, but there's other reasons that causes problems. So what the university decided to do is to make a building, and there we have beds, and people can sleep there overnight, and we can measure them, and then we have control over the data there. So there are medical doctors there, there are nurses in that building, and in this particular case, it is our Minister of Health having a sleepover at our building, getting her sensors, her health measured, and of course some AI on top of it. So why I'm saying you that? The reason is that what we see as big AI challenges, getting access to enough data, getting the data used in real world cases, is what we're trying to push towards. And there are other challenges with AI research as well. We all know that AI can solve tremendously complex tasks, such as medical diagnosis, but there's a lot of issues where we see AI research kind of coming to a short, and we see much of the research kind of stagnating, at least when we want to put it into practice. And one example of that is explainability, or we can even say interpretability. So can we really understand what the AI system is actually doing? It doesn't really matter that much if you're just using an app on and you want to use some social media AI there, you just trust it in some way. But if you want to do it in for wellness, for medical diagnosis, that type of thing, you understanding of what's actually happening, understanding the impact, maybe having it interpretable and explainable is really the key to building trust. Because no medical doctor in the right mind would say, I want to use a system. I don't really understand it at all, but I'll trust it. So that's not a medical doctor I know, at least. So this example here are of some cats. You probably see it. And it kind of explains a lot of what AI can and cannot do. So the first picture of this orange cat, this is not my research, but it's some famous research that is there. This is orange cat, and we can see that these well-known deep learning models, AlexNet, GoogleNet, is able to, with 100% accuracy on that data set, categorize this as a cat. Not surprising, AI is very good at categorizing cats from dogs. And we see that humans, 99% of humans are able to recognize this as a cat. I'm not sure the last percentage who's not able to see this as a cat, but at least most of them are. But the example goes further. In this case, we make the cat grayscale, and then we see that the accuracy of the AI systems go down a bit. And then we can make the cat a silhouette, and the accuracy of the AI system goes down even further, and we can make the edges of the cat only available to the AI system, and the accuracy is down to, at best, 40%. By the human accuracy of detecting this as a cat remains high, in this case 87%. So why? Why does this happen? Well, of course, the AI system has been trained only with normal looking cats, and it has no way of knowing that sometimes you can draw a cat in a completely different way and still it should be recognized as a cat, like this one. We humans, on the other hand, we have some sort of a very strong intelligence, meaning that we can expand beyond what we have seen in our training system. So even though I've never seen a cat like this, or a cat that is only a silhouette, I can still recognize it as a cat. But AI systems fail at that, and that is a fundamental flaw, you could say, in AI, that it cannot really expand upon the data that it's been trained for. Let me show you another example. This is from our research. We do research on nutrition, among other. And the idea is that when you're supposed to go on a special diet, you're supposed to lose weight for some reason, the nutritionists tell us that you should write down what you eat. And then they tell us also that people who do that, they lose interest in doing that after a couple of days, and they have a tendency to cheat a bit and maybe write down a bit less than what they're eating and all that sort of stuff. So the idea was you can make an app that take a picture of your food, and you can get the food recognized automatically with AI, typically something that AI could do. So this is a typical Norwegian breakfast, some cheese and some butter, etc. And then when my students were working on this, they told me that the system is able to recognize this picture as cheese, bread, grapes with 100% accuracy. Okay, that's good. And they told me also that it's able to calculate the amount of bread and the amount of butter. In this case, 4.4 grams of butter, 6.4 grams of cheese, and 38 grams of bread. And then I became very suspicious, because why can you at all recognize the butter that is 4.4 grams under the cheese there? It seems super intelligent in a way that is actually possible. It seems too good to be true. Even though they claim they could show all the graphs that it has a very high accuracy, my level of suspicion rose very quickly. And it turned out that our nutritionist collaborators, they not only put the information in Excel spreadsheet as they were supposed to do, but they also had some post-it notes on all of our pictures, And on those post-it notes, just to be nice to us, they wrote down exactly that it is bread, 38 gram, butter, 4.4 grams, etc. And when we looked closer into what the AI system was actually looking at, we saw that it didn't care at all about what was on the plate. It only cared about what was on this post-it note on the left-hand side. So it overfit, it overlearned from the system. And then if you only look at this post-it note, which is written in Norwegian, it's no problem. It's not hard to understand why it can understand that it is 4.4 grams of butter there, because it's actually written there. When we removed all the post-it notes, the problem became a lot harder. Not impossible, but much, much, much harder. And why does this matter for wellness? Well, we see the same type of flaw problem in some published research. In some cases, there's a diagnosis of cancerous moles, and the dataset has been skewed in some way that if there is a ruler in the dataset, in the picture, the chance of it being a cancerous mole increases a lot, simply because most of the moles in the dataset has a ruler next to it. when it's been taken, picture has been taken at a medical facility, while it's taken by other people, it has no ruler at all. But the fact that you actually add a ruler next to your picture does not affect whether or not you're sick. So why is that relevant? It's relevant because you skew the data in some way, and it kind of artificially learns how to be very accurate, but in truth, it is not at all. Let's move to another example. So this is Titanic. Probably most of you have heard of Titanic. And it's a ship that sank a couple of more than 100 years ago. And some people have ran an AI system to predict, can you predict with a high level of accuracy who will survive the Titanic crash. And of course, this is public data. You know a lot about the patients there, you know about their gender, their age, etc. So no surprise, the AI system could predict that very well. But then we could add some analysis, some statistical analysis on that data, more specifically something called Chapli Analysis. And we can, in a way, ask the AI system, what is the important factors about your prediction? So not only can you predict who will survive, but what is the features that you think is relevant, think in quotation mark, for doing an accurate prediction. And in this case, the AI system claims that the gender or sex of the person is the most important. Second is the class. Third is the age, etc. So, for example, if you're a male, the chance of you surviving is a lot less than if you're a female. And if you're a first class passenger, the chance of surviving is a lot higher than if you're a second class or a third class. So Leonardo DiCaprio, for example, who is a male and a third class passenger, would, according to this AI system, not survive. But the other person, Rose, female, first class citizen, will survive according to this system. And why is this important? Well, this adds a level of explainability on top of the accuracy. So that means that we can understand much more about what is actually happening in such an AI system, and that makes it much more useful for medical doctors to use in practice. We can just see a more complex example of the same. This is for predicting the presence of Alzheimer based on cognitive tests. The AI system can predict fairly accurately who has a mild cognitive problem and who has Alzheimer. Not perfectly, but very well. That's not the reason for this graph. The reason for this graph is what is the impacting factors in this AI system. Well, in specifically this system, it is the presence of cognitive dissonance, cognitive problems. That's the most important factor. Age is the second most important factor. Presence of the POI protein, third most important factor in this AI system. And we can see that this makes sense. Age is something that we closely relate to the presence of Alzheimer because it mostly happens to old people, not young people. Cognitive problems is something that we relate to Alzheimer, so that is, of course, relevant, but not all cognitive problems are or cause Alzheimer. There's a lot of other cognitive issues also. So I think explainability or interpretability is key to making AI systems adapted into real world life. Because Pricewaterhouse, they did a survey a couple of years ago, and they asked, do you trust using AI in your healthcare system? So they didn't ask exactly where as a diagnosis or anything like that, just in general, do you trust using AI? And 39% said yes, and the remaining 61% said no. So about 1/3 trusts having AI in their system, about 2/3 say not at all. Then they asked a different question. What about if you have an AI system for your significant other, your spouse, and then the chance or the agreement of using AI increased to almost a half? What does it mean? Well, AI is okay, but mostly not for me. As long as it's for my wife, it's totally okay. So that means that people trust AI in some sort of way, but they have some reason to have a way to think that this is not really something that is completely solved, something we should trust, but it is coming along. My famous example is about data handling, I think. So my favorite example is about data handling, and this is we do some work on Alzheimer's prediction from images, MRI images, and it is very challenging to get very good data on this, but we don't really need to collect our data itself. The reason is that there's a big US research project called ADNI working on Alzheimer, and they've said what's most important to us is to solve the problem of predicting Alzheimer, and they made all the data publicly available to the audience out there. So what has really happened is that there's a lot of high quality data with MRIs of people. Some have reached Alzheimer, some have not reached Alzheimer, and some have had a drinking problem, some have had a sleeping problem, some have had a drug problem, and all that thing is anonymized but still in the data. And what has happened in practice is that there's a competition among a lot of researchers to be the first to have a very good prediction of Alzheimer based on MRI on its metadata. So data sharing is key to really pushing the AI research forward. There's researchers all over the world working on that data that is quality assured and collected from US patients. And that is kind of what we're trying to do as well. So we're doing it with colonoscopy, highly quality collected data from another research organization called Syntab in Norway. And then we have open competitions on exactly this. This data is quality assured. It is given, it's anonymized in a high quality way. And then the task is put out so that researchers, mostly Norway, but other places also, can develop their algorithms without thinking about data handling, thinking about all the other part that typically will be in such a system. And that also includes using synthetic data, which was on the last talk before me, in this case on ECG. So can you make a synthetic ECG signal that resembles the real one so that it becomes anonymized and then can be used without having to have a privacy breach of the system. That makes it much easier to share data among people, to put it online on the internet when the data is only synthetic, because there's no reason to believe that patient-sensitive information will be leaked in that way. And that's what we think is crucial when we also do our age-related macular degeneration research. That means looking at the back of eyes together with medical doctors in order to understand what causes the blood vessels to break in a specific way and detecting it early. In this case, there's a strong collaboration between medical doctors, eye experts, and we who are deep learning neural network experts working on that problem. They have a lot of experience in eye diseases. We have experience in understanding machine learning and data sharing, making that data available to the public is highly relevant, I would say. Another type of research we do is what we call the home service for people who are typically elderly but have some many diseases at the same time, comorbidity. There's a lot of patients that have COPD from smoking and other lung diseases, and at the same time they have some heart problems and a lot of it at the same time. Then each patient becomes very complex, and it's hard to really say it's a single disease that you want to diagnose. So what we're doing here is that we do AI prediction of how the patient will be affected by the disease in the next day, the day coming or the day following, and the day after that. And the reason we do that is not to say to tell you will become sick soon, but to make sure that the nurses that go out and visit people at their home can really understand how to prioritize. Because if the system goes produces an alert, you should prioritize that patient that has that type of predicted worsening of the disease. Because most of the existing systems are just based on threshold values. If your pulse is this high, or if your blood pressure is this low, then there's an alert. But all medical researchers tell us that it's more complex than that. Of course it is. It's not based on common thresholds, but it is. It all depends on what you've been eating that day, what you've been, if you've been near a bonfire, for example, that type. So the secret here is, of course, to make sure that the AI system is a decision support tool for those with medical expertise. Other research that we're doing is in psychiatric work, and that is meant for teenagers that have psychiatric issues or want to have psychiatric questions. There's a lack of psychiatrists that could help these teenagers, and they tell us that there's a lot of these questions that are the same for many of the patients, and they're not that serious, but then there's a lot of questions that are very serious, and they want to focus on those that they need a lot of attention to. And the idea is that you filter out and say these issues here are very important, that you talk to a real human psychologist, and these questions here are normal teenage problems that you can get a robot to help you with. Not to automate completely, but to kind of help you in some relatively simple way. And what it turns out that these students or these teenagers that work with use the system, they not only trust the system, but they trust it even more than talking to a medical doctor, because it's somehow anonymized when there's a robot there doing the analysis instead of a real human there. So you see that the patients are really opening up even more because they're talking to an AI, not despite they're talking to an AI system. The chat system is simple, but key to it is to detect whether something is really, really problematic, and you should then contact a real life person there as well. Some of the other research that we're doing is analysis of medical patient journals. And that means that it becomes decision support tools to medical doctors, and to develop a system that looks very similar to the system that they already have in place, and then highlighting important information in a complex and large medical journal. And that is important because some of these medical journals are enormous, so thousands of pages sometimes, and it is unrealistic to ask a medical doctor to read all of that before an emergency operation, for example. But to get some important parts highlighted so that they can look at it more closely. So in this case, it's about allergies. Here is a person that is allergic to penicillin, and it's not only looking at the word penicillin, of course, but sometimes this is written as allergic to, sometimes it's written as reacting to, and sometimes it's written in a very, very different way. So last point I wanted to make before I reach the conclusion of my project is the presentation is that we see this huge need for data, and we see this advance in what's called semi-supervised learning. Semi-supervised learning is that you make up some sort of game, some sort of puzzle of your data, so that you can learn only without the need for doctor supervision of the data. So in this case, you have a car, you make a puzzle of it, and the AI is supposed to puzzle it back. And we see that research not only for cars, but for things like prostate cancer and other tumors in the brain thereabout. So the obvious secret to making AI for wellness is three things, as I see it. It is to have a concrete and measurable problem. You need a problem that you can mathematically define in some sort of way. It is to seek the power of your data. You have a lot of data, understand what the power is of it and understand what it isn't. Share the data if you can and use share data. And I would say most importantly is to understand the problem and the process itself. And that understanding is both about understanding the algorithm, what it does and what it doesn't do, how does it influence, what does it really mean when it does something, and understand the problem, which then means often in our case the work for medical doctors. Thank you.
Morten, thank you very much. I could listen to you for a lot longer. It's been extremely interesting. Did you want to say something else there? Are you okay?
No,
okay. A lot of questions coming in, and a lot of people, I suppose, curious about more and more information. And I suppose as you talk and we hear the complexity of the body and the mind in itself, without even bringing in the AI, and the AI combined really creates opportunity for a lot of innovation, really, and a lot of challenging thought process being put forward there. And certainly, I suppose, listening to you there talking about the youth as well, and we look at post-COVID now and done some research there previously, and the implication it's having for their mental wellness, and curious in the fact that they trust the anonymous AI person more than the real person. It's really does present opportunity and challenges.
Absolutely, but it's not that surprising, because when I have something wrong with my body, the first thing I do is to Google it, right? It's anonymous, fine. Yeah. And then, of course, if it becomes really problematic, I call my MD. So it's the anonymized, fine way of using a system. Yeah.
Okay. Again, I'd love to talk to you about more on that, and maybe another time. But some of the questions that are coming in, Fran is asking the question regarding how is the density of the cheese bread measured through a visual tool?
All right. Okay. So it is measured using something called semantic segmentation, and that means that we pixel-wise find out where the cheese is, where the bread is, where the butter is, and then there is a well-known, or there's a table basically saying that if you have cheese and this amount of cheese, given the ruler of this size, then you can calculate the grams and also the energy that is used. So the actual calculation of the energy of cheese, calories, is calculated just from a simple table. The presence of cheese is just pixel-wise amount of cheese and butter, etc., and that is there. So semantic segmentation, a technique called YOLO, is very relevant there.
Okay, thanks, Morten. Another question coming in from Liam asks, what are the ethical challenges you have to overcome when gathering the data, and where do you source the synthetic data from?
Well, there's of course ethical challenges with data collection, but I would say many of them are solved by anonymization, and some of them are solved by having the AI run at the hospital instead of having them run at our university. So what we do is we develop the system and then we push it to a computer at the hospital, and they have all the security in place. They have all that in place, and then we don't have to ask the patients for confirmation that we can use the data, because it is then part of the medical hospital system that is there. So if I were to ask to do that on my own computer in the university, I would get that data and I would need to ask permission from all 500,000 patients in that system. That's unrealistic, really. So what we do is we have a small set that we've asked permission for. We train it locally and then we push it to the system and at the hospital, and then we test it out there. So I would say the ethical parts of that is maybe when there's put restriction into place that says that we cannot use it. There's some politicians that say that we're kind of breaching privacy issues there, that not asking permission to use AI on their system, and that is a bigger ethical challenge, I would say, than actually using it, because the medical doctors, they tell us this is a helpful tool, it potentially saves lives, and that is not using is a bigger ethical issue than all of them. But you can of course talk about privacy and all of those things. That could be issues as well, but we don't really reach them, I say.
And the other part of that question was, where do you source the synthetic data from?
Oh, right. So there's different synthetic data. I think most relevant was the prostate the synthetic data, maybe, that I talked about at the very end. That was that is based on an open data set. That is synthetic. Now that is publicly available, and then we use something called a generative adversarial network. It's kind of a GAN. You kind of play a game with the system to make data that looks like that data, and then we get the synthetic data from there. So the ECG data, that is synthetic data from patients, and then we do the same type of generative method, make the synthetic data that looks like the real data, and then we ask the medical doctors, can you see any difference between those? And they say no, and then we push it out and we say it out. So the prostate cancer is data that is public data set somewhere. The ECG is some medical hospital data that we have at the hospital. Yes. Mm.
Thanks, Morten. Another question coming in from Andy is if you could elaborate on the point of seeking the power of your data. If you could elaborate a bit more on that.
Right, sure. So what I mean by that is to understand what is the value of the data. It means that trying to say in, let's say, medical diagnosis, there is some relevant factors that are there. There are some relevant factors that are not there. For example, if you there's in GDPR, there's something called data minimization, and that means that you should select beforehand what are the relevant parts of the data. So that is not seeking the power of data. Seeking power of data is to push the data into a system and then let it ask itself what is the relevant factors, and then see through scientific methods what is how accurate is it really doing. So I would say seeking the power of data is to understand what data you have, and then trying to do methodically correct way of doing it correctly.
Okay, we have one more question. There are a lot more questions, but we're just going to have time for one more because we're almost out of time, Morten, if you don't mind taking this last one, where David has asked, what's the future challenges your research will look at? What are the future challenges of your own research right now?
Well, we're looking at multiple sclerosis now. We've just applied for some funding. Hopefully the Norwegian Research Council agrees that is what we should do research on. And that is challenging for several reasons, because the data set is smaller, so the smaller data sets, and it's challenging because it's not clear from medical point of view what causes that. In Alzheimer, there's some plaque in the brain. Multiple sclerosis is something more complex. So that means that we add a level of explainability. So maybe it can even push the research of medical research as well, saying that when this person develops multiple sclerosis, it is because of this and this and this. So hopefully that is some of the future research that we will be doing.
There are further questions, but I can see Radine is getting anxious for us to move on to the next session. But if we could very, very quickly, Radine, if you don't mind, we've got 2 or 3 minutes left to go, if that's okay. Neja has asked that the techniques of data augmentation depends on the task, classification or segmentation.
Yes, so if the techniques of data augmentation depends on the task, sure it does, because when you do segmentation, you need to label it in some way, and the labeling of segmentation means pixel-wise, saying this and this and this pixel is cheese, this and this pixel is not cheese. If you do classification, you just need cheese, not cheese. So it depends, absolutely. But I think for the augmentation part, it's not that different, because we don't really do data augmentation that much for segmentation. We could, of course, but I think it doesn't matter that much, I think, as far as I can tell, because you push it into the same generative network. Of course, it's the mathematics might be a little bit different, but not that much. So we say data augmentation is at least very similar depending on the task. I would say not identical, to very similar.
Okay, Neja, I hope that has helped answers part of the question that you've asked, and I'm sure there'll be an opportunity to follow up subsequently on this. So at this stage, for me to say, Morten, thank you sincerely. The time flew by and could go on and on. There are more questions coming in, but we can forward them on to you directly subsequently. Thank you indeed, and enjoy the rest. I'm sure you're staying with us for the rest of the summer school, and it's now back to you, Regine. Thank you very much.